Hi everybody. So this next section is on exponential and logarithmic equations. And I know we've looked at these a little bit already, but we're going to look at solving sort of some more complicated versions of these. And we'll see, we can basically use the laws of logarithms to solve a lot of these problems. So one thing I want to mention here is the one-to-one property of logarithms. And basically all this says is that if you have two logs that are equal, then their arguments have to be equal, right? The thing inside the logarithms have to be equal. So for example, let's say you want to solve this equation. Well, remember we have those properties of logarithms that said if you have log of something minus log of something else, you can combine those together, or you could also move this log over to the other side, and then log base 5 of 1, that's just 0. So you get log base 5 of 8 is equal to log base 5 of x. And so you would get x is equal to 8, and then you can check that if you want. I suppose another way you could do this one also, like I said, is using the laws of logarithms. You could write this as log base 5 of 1 is equal to log base 5 of x divided, divided by 8, because, again, you can combine them together like that. And so you'd get 1 over x is equal to 8, multiply both sides by 8, and you would get x is equal to 8. So that would be another way you could do that one. But the important thing here to realize is that if you have two logs that are equal, right, they have the same base, then the thing inside the logarithm should equal the thing inside the logarithm there. So let's look at another logarithmic equation. So this one, again, we're using that property that says if you have log of something minus log of something else, provided they have the same base, you can just write that as the log of the first thing divided by the log of the second thing, right? And then we can use our properties of logarithms to rewrite this and write this as 3 raised to that power. This base raised to that power has to equal the argument of the logarithm, and then just solve that equation, right? It's a rational equation, so multiply both sides by x minus 1, and then just distribute the 9 through there. So you'll get 9x minus 1, or minus 9, right, will equal 4x plus 6. And then you have 5x is equal to 5, so x will be equal to 3. And then again, if you want to check your answer, right, put 3 back in for all the x's there, you should get 2, right, which you do if you check it out. Okay, so just to kind of generalize this procedure, talk about what we did for these, to solve a logarithmic equation, then what you want to basically do is try to get the logarithmic term if there's only one on one side of the equation. And you might need to combine logarithmic terms like we did for this one, where we combined these by dividing by the quotient property. And then try to write the equation in exponential form, and then solve for the variable, right? So that's what we did here. We wrote it in exponential form, and then we just solved for x. So let's maybe look at some more of these just to show you how this works. So so for example, let's say you have log of x is equal to 3, right? Remember, the base here is 10. You've already got the logarithm isolated, so all you have to do is write that in exponential form, right? So you'd have 10 to the third is equal to x, so that means that x must be 1,000, and if you check that, right, log of 1,000 is 3. Right, for this one, again, we've already got the logarithm combined together on one side, because there's only one logarithm, so you'd have 3 to the third is equal to 2 minus x. And so you get 27 is equal to 2 minus x. So subtract 2 from both sides, right, and you'll get x is equal to 25. And if you do plug that in for x, that will work out, right, because 2... oh, sorry, that should be a plus 25, right? Sorry, that should be a minus 25. So if you have 2 minus a negative 25, that's log base 3 of 27, and that equals 3. This last one is pretty similar to this other one we did. Right? You want to sort of combine the logarithms together. So just to remind you the steps, right? Try to get all the logs on one side, and then combine your logarithms together, and then write it as an exponential equation, and then solve. Right? So for this last one, right, you could write this as log base 5 of x plus 1 over x minus 1 is equal to 2. So you'd have 5 squared then is equal to x plus 1 over x minus 1, writing it in exponential form now that we've got all the logarithms combined together again. So you would have 25 is equal to x plus 1 over x minus 1. Multiplying both sides by x minus 1, you'll get 25x minus 25 is equal to x plus 1. And then solve for x, right? So if I subtract an x from both sides, I'll get 24x. If I add a 25 to both sides, I'll get 26. So I'll get x in this case will be equal to 26 over 24. You can reduce that to what, 13 over 12, I guess. And so again, you can check that and see if that works. And one thing you got to watch out for these logarithmic equations is you got to make sure that it doesn't make the argument 0. Now x itself can be negative like we saw here, but you know, like for example, if you take 13 over 12 minus 1, that should still give you a positive number, right? But if you ever get an argument that's negative, remember the logarithms aren't defined for negative numbers, right? Then that's no solution. So let's maybe just look at some other examples. So let's say you wanted to solve this equation. Well, this would be very similar to the one we just did, except you'd want to add these together. And I suppose you could also move the logarithm over here. But remember, if you've got a log on both sides, the argument should be equal. So let's just leave this one over here, but you could move it over there as well. So at least combine these two together, right? So you can write that as log of x plus 3 of x, right? That's the argument of the logarithm. And then again, because they are both base 10, right, the argument here should equal the argument there, right? So multiply the x through, you get x squared plus 3x equals 4. It's quadratic, so make one side 0, factor, and then that means that x could be either minus 4 or positive 1. Now again, you want to make sure that you check that, right? If you check negative 4, right, I don't think that works, right, because you'll get log of a negative number, right? That's what I was just talking about in the last example. If you get log of a negative number, then that can't be a solution, right? So the only solution in this case is x is equal to 1. So it isn't very important for you to check your answers for these, just like the rational and radical equations. Okay, so that should give you an idea of how to solve logarithmic equations. The next thing we want to look at is solving sort of more complicated exponential equations, right? I know we've already looked at some of these. You know, like if you had say like 3 to the x was equal to 3 to the 2x plus 5. Again, because the bases are the same, you could just set these equal to each other, and you'd get x is equal to 5, right? But now we're going to talk about more complicated equations, and again, we'll basically use the properties of logarithms, the third property, to bring down the exponent in front. So for example, let's say you want to solve this equation, right? It's pretty hard to write 23 with base 5. So what we're going to do then in this case is we're just going to take the log base 5 of both sides. So I'll take log base 5 of this side, log base 5 of this side. And the reason why I'm choosing log base 5 is, remember, if this number and this number are the same, they cancel each other out. I guess you could also think of bringing the x down in front, and then log base 5 of 5 to the first would just be 1. Either way you think about it, this side should be x. Here you'll get log base 5 of 23. Now remember that some calculators will do this, but if your calculator doesn't do base 5, right, remember you just take log or natural log of 23 over log of 5, right? Either use the log or natural log, and that'll give you about 1.948. And then if you want to check and see if that's right, plug that into the exponent and see if that works. Now for these problems, the answer should always be the answer unless you make an arithmetic mistake, right? Unlike the last one where you got an extraneous solution. But again, it's always a good idea to check your answer anyway. And depending on how you round this number, you may not get exactly 23, but it should be pretty close. Let's look at a slightly more complicated example. So here again, I'll take the log of both sides. And I could take log base 15, but I'm just doing log base 10. Now remember, that will allow us to bring the exponent down in front, and then we're solving for x. So divide both sides by log of 15, and then go ahead and, I guess, calculate this. Use your calculator. Or you could move the 2 over first, but let's just calculate this. And then add 2 to both sides. That'll give you 3x is equal to 4.008116. And it's hard to tell how many places to round this to. Hopefully I'll tell you in the homework or the exam. But if you have questions about that, don't be afraid to ask. And then finally divide both sides by 3. Right? And then again, you can check that by plugging that back into the original equation, and you should get the same thing on both sides. Okay, so you can see these are all kind of the same. Here, let's just do some other examples. So let's say, for example, I want to do log base 5 of x is equal to 27. Well, that'd be similar to the one we did before. Again, I could do log base 5, but I'm just going to do log base 10 here. Bring the x down in front, and then divide both sides by log 5, and so x is equal to that. And this is the exact answer. You know, you could leave it like that, but if you want to approximate it, right, that would be the approximate answer. For this one, you probably want to divide both sides by 3 first. That might make things a little bit easier, because if you take the log of this side with that in there, you can't really bring the exponent down because it doesn't apply to everything in there, just the 2. But now that you've done that, then you can take the log of both sides. So I'll take log, any base you want, really. Doesn't really matter. So take the log of both sides, and then again that allows me to bring the x plus 1 down in front, and then I'll get log of 2 is equal to log of 3. So then I can basically just divide both sides by log of 2, and then x then will just be log of 3 over log of 2 minus 1, right? And you can use a calculator to get a decimal approximation for that if you want. For this one, you don't really have to take the log of both sides, right? I mean, because the bases are already the same. So you can take the log and get the answer that way. But if you see something like that on the exam, just do it the old way. It's probably easier. You just get x is equal to 1, right? And now for something like this, again, you want to take the log of both sides. So you'll eventually get x times log of 3 because that exponent will come down. Same thing here. You'll get the 2x plus 1 come down in front of the 2. And then just solve that for x. So you've got x log 3 on the left side. On the right side, if I distribute that log through, I'll get 2 log 2 x plus log 2, right? So I'm just taking the log 2 times the 2x and the 1. So again, we're solving for x, so get everything with x on one side, right? So I'm just going to move the 2 log 2x over here is equal to log of 2. So just move that over to the other side. And then go ahead and factor out your x. So you'll get x times log 3 minus 2 log 2. Right? So I'm just pulling an x out of each term there on the left. And then I'll get log 2. And then finally, to solve for x, just divide both sides by whatever the x is being multiplied by, namely this, right? So just divide both sides by log 3 minus 2 log 2, and then that's your answer. Again, you can use your calculator to get a decimal approximation for that, but a lot of times you can just leave your answer in exact form like that on the exams anyway. Okay, well, let's look at maybe a couple of applications then of exponential and logarithmic models or equations. And some of these we might have already looked at before. I think we might have looked at this already. But so remember, the compound interest formula is given by A equals P times 1 plus R to the N to the NT, where P is the principal, that's the amount you're investing. N is the number of compounding periods, usually per year. T is the number of years, and R is the annual interest rate. So suppose that you deposit $2,500 into a certificate of deposit today. If the deposit earns 4% interest compounded monthly, how long will it take before the CD is worth $4,000, right? So the idea basically is we want to solve for T. So if you think about this, this is an exponential equation, right? So just plug the corresponding numbers into the equation, plug 4,000 in for A, 2,500 in for P, that in for R, and that in for N. And then we have to solve that equation for T. And so plug all that stuff in there. Then just go ahead and simplify this, right? So I'm going to divide both sides by the 2,500. So 4,000 divided by 2,500 is 1.6. If I take 0.04 divided by 12, that gives me 0.003. So 1 plus that is 0.003. And then remember, we want to solve for t. So this is an exponential equation. So I have to take the log of both sides, just like I did before. Now this 12t applies to everything inside the logarithm, so that I can bring down in front. And then divide both sides by log of 1.003, so I'll get 12t is equal to that. And then finally divide both sides by 12, and I'll get t is approximately 13 years, right? It might not be exactly that, but it should be pretty close. Right, so here's an example of where you might use an exponential equation, right there are the methods for solving exponential equations to get an answer, right? You might want to figure out how long is it going to take for your money to grow from $2,500 to $4,000, right? It'll take about 13 years. Right, so maybe you're trying to save up for a down payment on a house or something, and you're trying to figure out how long is it going to be before you can buy a house. I don't know what that's doing in there. Let's look at some other types of problems that you might encounter. Some books will cover these and some won't, but I did want to just cover some other types of exponential equations, because not every exponential equation is going to be solved with the techniques we've used before. Like, for example, this one, you can't really get the x's down in the same level as everything else. But if you look at this one, if I rewrite it, this is actually sort of a quadratic equation in disguise. So you can think of this as, you know, u squared minus u minus 6. So you could actually factor this into e to the x and e to the x, and then minus 3 and plus 2 is equal to 0. So you'll get e to the x is equal to 3, and e to the x is equal to negative 2. And then you can solve that by just taking the log or natural log of both sides. I'm just going to use the natural log because we're working with e. So if I take the natural log of both sides, I'll get x is equal to the natural log of 3. And here I'll get x is equal to the natural log of negative 2. Now remember, you can't take the log of negative numbers, so that means the only answer there would be the natural log of 3 there. Here's another example with an exponential equation in it. So this one, you might notice that all the terms have a 10 to the x in them. So try to factor that out first. That'll leave you with x squared minus x. And then if I move this over to the left-hand side, I'll be left with a minus 2 is equal to 0. Now, if you think about it, there's no way that 10 to the x can be 0, because remember, exponential functions are never equal to 0. No matter what number you put in for x, even if it's a negative number, it's never going to be 0. So the only way this can be 0 is if this thing is 0. And if you factor that, you'll get x minus 2 times x plus 1 is equal to 0. So it looks like the solutions for that would be x is equal to 2 and x is equal to negative 1. Okay, so it's just some weird ones that you might run across. If you have trouble with those, let me know. Let's look at some other examples of using exponential and logarithmic equations. So let's say that the population of a city is currently this much, and you want to find the relative growth rate is 9% per year. Find a function that models the population as a function of t. Project the population 15 years from now, and how many years from now will it take the population to reach 200,000? And the model we're using in this case, again, is we've got the initial population, the growth rate, and the time. And so we're assuming that it's growing exponentially. So again, for this last one, we might have to solve an exponential equation, right? So for the first one, here's our equation, right? This is the initial population. That's the growth rate. For the second part, right, we want to figure out what is the population 15 years from now. So put in 15 for t and work that out. Now for the last problem, we want to figure out when is the population, right? When is n of t going to equal 200,000? So in that case, we have to put 200,000 in for this, and then we have to solve for t. Well, what sort of equation is this again? Well, this is an exponential equation, just like the one with the CD we did a few minutes ago, right? So how do you solve that? Well, again, basically, take the natural log of both sides or something, right? Or log base 10 or whatever. So again, just to simplify this, I'm going to divide both sides by the 139000, right? Then I can take the natural log of both sides. Now, because remember that natural log and e are inverses of each other, they'll just sort of cancel each other out. So you'll get 0.09t. And then to get t by itself, just divide both sides by 0.09. If you solve that, put that into your calculator, you'll get about 4.04 years, right? So again, there's another example of where you might want to use that to solve an equation, right? So maybe you're an urban planner and you're trying to figure out, how many years is it going to take for the population to reach this amount, and how much sewer and roads am I going to need to build to accommodate that many people. I guess we already kind of looked at this one. And I guess we already looked at continuous compounding. I think we'll just skip this example. But remember, if you're compounding continuously every possible moment in time, right, remember that you get this equation. And the reason why, again, was because of that. I think we already looked at that. So if you wanted to find the amount of money accumulated if you invest $1,000 for 60 years at 2.5% interest, right? Remember, you'd want to use this formula if it's compounded continuously, not the other one. Right, so just plugging that into the formula there, right, you should get an answer. So I could, let me maybe just work that out quick. I don't know if I've done that yet, but so basically take, so make sure you work out this exponent first, right? So take 0.025 times 60, and then raise e to that power. So I think that'll give you about 4.481, something like that. Oh, got to take it times 1,000, right? So about $4,481.69, something like that. Hopefully that's the right answer for that one. But, another place where you might see exponential equations and stuff is radioactive decay. So if you have radioactive substance decaying over time, the equation will be given by this, where R here is what's known as the R is the natural log of 2 divided by the half-life. Right, the half-life is the amount of time it takes for half of the substance to not be radioactive anymore. So let's say that some aluminum-238, I don't think that's an actual element, but has a half-life of 50 seconds. So that means after, if you have a radioactive substance, after 50 seconds, half of it will no longer be radioactive. And then 50 seconds after that, the part that's still radioactive, half of that will no longer be radioactive. How long will it take for 90% of the sample to decay, right? So in other words, we want to keep going until only 10% of the sample is radioactive anymore. So again, you take your exponential equation, so just going back to the model here, right? So we have the initial mass in this case. I guess we don't know what that is, but you could think of it this way, right? We're going to have 10% of the original mass is equal to the original mass times e to the minus RT, right? Because we want to keep going until only 10% of that is radioactive. So you can really actually cancel the two masses there. It doesn't really matter. So you'll have that equation, then you'd want to just solve that, right? So in this case, and again, maybe I should clarify what this is, right? It may look like the t's in the bottom here, but this is the natural log of 2 over 50 times t, right? So here, again, I'm going to just bring the negative up on the 2, and then just go ahead and solve this for t. And something doesn't look right there, but anyway, so you'll get the e and the natural log will cancel each other out, and so you'll get this equation, and then 2 to the negative 2 to the or 2 to the negative 1 divided by 50 is 0.987, and then just take the natural log of both sides and bring the t down, and then just divide, right? It shouldn't take very long if you think about it, but it'll only take 332.19 seconds. You can kind of estimate that too if you want to double check, right? I mean, so after 50 seconds, 50% of that is no longer radioactive, right? So this part won't be radioactive anymore, and you'll have that part. And then after another 50 seconds, right, half of this will no longer be radioactive. So that'll be about 25%, right? So that'd be 50 seconds plus another 50 seconds, which would be about 100 seconds. And then after that, right, only about 12.5% of that would be radioactive. So that would be another 50 seconds. And then, oh, something doesn't seem right there. This should be closer to 150. What did I do wrong here? Let me maybe work this out again here. Maybe I made a mistake with my... So 0.01 equals e to the... So you should always check your answer here too if you can. So this is 50t, and Oh, I should have brought the 50 up on the 2 also, right? I guess I could bring the t up there too. Yeah. So let me maybe rework this one. Maybe I made a mistake here. So so you can think of the negative 50 and the t as being multiplied times the natural log. So you can actually bring those up as an exponent on the 2. So I can bring up the negative t over 50. So the e and the natural log will cancel there. So I'll get 0.10 equals 2 to the negative 50 to the tth power. So let's see, so 2 to the negative 50, what's that? So if I take 2 and raise that to the negative 50, that doesn't seem right. 2 raised to the okay, yeah, so that'll give me 0.10 equals 0.123456 7 8 9 10 11 13 14 15 8 8 817, something like that, t. So then take the natural log of both sides. So I'll tell you if that's right. So I'll take the natural log of that number. So bring the t down, then I'll take the natural log of that, which would give me minus 34.657. And then if I take the natural log of this side, 0.10, take the natural log, I'll get negative 2.302. So I'll get t. So divide this number by that number. That still doesn't seem right. Well, something's not right there. I'll have to double check and see what's going on there. But I made a mistake here somewhere. But the idea again is you want to take the natural log of both sides there. Sorry about that. I'll try to work through that and see what happened with that one. So one other thing I want to talk about is you can also solve logarithmic and exponential equations graphically. It's a little bit harder to do that, but like, you know, so for example, if you solve this one algebraically, right, you want to move the natural logs over to one side. So you'd get minus log 5 of x minus 4 is equal to 1. And then these you can combine together because you're dividing, so it'd be x over x minus 4 is equal to 1. And then just go ahead and write it in exponential form. So you'll have 5 to the first is equal to x over x minus 4. Multiply both sides by x minus 4. You'll get 5x minus 20 is equal to x. And so moving the x over here, you'll get minus 4x. You'll get x is equal to 5. Now another way you could do this also is you could take the log base 5 of x, which if you graphed it would be given by this, and you could take log base 5 of x minus 4 plus 1, which is given by this, and you could just look and see where they cross, right? What's the x-coordinate there? Well, again, this is not as precise, because again, it's kind of hard to tell exactly where they cross, is that, you know, it looks like it's close to 5, but, you know, maybe it's 4.9 or 5.1. So in a way, the algebraic method is superior, but if you can't solve it algebraically, you might also be able to solve it by graphing both sides and seeing where the heights are equal, right? That's what it means to solve. Okay, well, hopefully that should give you guys an idea of what to do for that section. So if you have questions about that or anything else, make sure you let me know.